Okay, then please go ahead. You're ready.
Okay. So yeah, I'm Kazuhiko Minematsu from NEC Corporation, the chair and Sumanta Sarkar, and we will host this session. Okay, we have 5 talks, and each talk will consist of a 5-minute short presentation and a subsequent Q&A session, probably in 7 minutes. But you can ask. You are expected to post a question on the Zulip, as you can find from the website of the Asiacrypt. Then we will assign we will ask the question to the presenter. Okay, that's procedure. So okay, let's start with the first talk. It is entitled as a practical key recovery attack on 805 round Trivium, and Chen-Dong and Tian, and Tian will give us a talk. So please start.
Okay, I will give this live talk on our paper. This is the outline of this talk. First, let us briefly introduce Trivium. Trivium is one of the extreme hardware-oriented finalists. It was specified as an international standard. Both the key size and IV size are 80 bits. The size of the internal state is 288. This is an overview of the key stream generation of Trivium. The internal state can consist of 3 nonlinear feedback shift registers. The feedback functions are quadratic. And the output bit is obtained by the exclusive ORs of 6 bits from the internal state. Before the first keystream bit, the whole state should be initialized for 1,152 rounds. There are 4 important attacks on Trivium. They are cube attacks, division property-based cube attacks, correlation cube attack, and conditional differential attack. In this talk, we focus on cube attack. We introduce some basics of cube attacks. In the cube attack against tree cipher, the first output keystream bit is described by polynomial in key variables and every variables. Choose a subset I of every indexes. Then Ci is a cube, which is a set of assignments for every variables consisting of 2 2D tuples, in which the variables indexed by I are active variables, which means they are assigned to all the possible combinations of 0 and 1, while all the other IV variables are assigned to 0 or some fixed constant. Then the summation of the function f on the cube Ci will give the superpoly of Ci on key variables. There are 2 states in the cube attack. One is offline phase, which is independent of the secret key. The other is online phase. In the online phase, we will solve a system of equations defined in key variables. In the offline phase, the main aim is finding some useful superpolys in secret key variables. And then the most important step is finding useful superpolys in the offline phase. Then there are 2 basic problems in cube attacks. One is how to find a good cube. Here, a good cube means the superpoly is low degree or balanced. And the second problem is how to recover the ANF of the superpoly for a given cube. There are many works on how to recover the accurate ANF of the superpoly. According to how you recover the superpoly, the cube attacks generally are divided into 2 types. One is experimental cube attack, and the other is division property-based cube attack. In experimental cube attack, superpolies are recovered by probabilistic tests, such as a linearity test and a quadratic test. While in division property-based cube attack, the superpoly is recovered by division property. At Crypto 2017, Todo first introduced the division property into the cube attack against the street cipher. But before Eurocube 2000, Hall introduced the three subset division property. The accurate superproperty could be recovered by division property since Eurocrypt 2000, which means that we could recover the accurate superproperty by division property using three subset division property without unknown subset. Now we have, I think, how to recover superproperty is well established in Cryptanalysis. At this stage, it is difficult both for experimental Cryptanalysis and division property-based Cryptanalysis to recover lots of superproperties with randomly selected cubes. For experimental Cryptanalysis, testing a cube of size larger than 40 is very time-consuming, and you need to test a lot of cubes to find one useful one. For three subset division property-based Cryptanalysis, though it could treat large cube size, the speed is mainly decided by the scale of the superproperty. For random cube, it is still very large. To further improve efficiency and increase the number of rounds vulnerable to Cryptanalysis, we need an effective method to construct useful and good cubes. Our aim of this paper is to construct cubes for recovering linear superproperties. The main idea is starting from a set of cube variables indexed by I and extend I to be a large candidate cube indexes. In this paper, there are three main algorithms. One is an algorithm to predict the preference bit for a given round. The second is a heuristic algorithm to construct candidate cubes. The third one is the improved Möbius transformation to reduce storage complexity. For to construct a start cube set, we observe that the output bit is exclusive OR of 6 bits from the internal state. If a cube C has a linear superproperty, then it is likely only one of the 6 terms works. And the other 5 terms contribute constant 0. This is because for Cryptanalysis against Trivium, the linear superproperty is very sparse, usually only one variable. Then we give an algorithm to predict the preference bit. Assume S66 is a preference bit, then we write its feedback function and come back to the time stance t minus 66. Choose a set of cube variables indexed by I and search some of its subcubes to find a cube with linear superproperties either in S286 or in S287. Such cube is a starting cube set. Then we extend a starting cube to a large cube. First, add every variable to I, which makes the degree of the superproperty decrease as fast as possible. Then we found that sometimes the degree drops from 10 suddenly to 0. Then we come back and add every variable to I, which decrease the degree of the superproperty as slowly as possible, make it to near degree 1, a linear superproperty. As for the improved Möbius transformation, actually, we do not to make a Cryptanalysis. We do not need the whole Möbius, the whole truth table, because we only use large cubes. For a cube of size 40, maybe cubes whose size over 38 may be useful. The other cubes are not useful, so we propose to breaking the original Möbius transformation into 2 stages. First, we treat several sub-functions and only keep useful information. When we applied our method to Trivium, we find more than 1,000 cubes with linear superproperties in output of 805 round Trivium. And there are 38 independent linear superproperties could be used to recover key information. We also find 16 linear superproperty for 806 round trivial by only sliding the cubes for 805. This is a summary of the Cryptanalysis on experimental Cryptanalysis and division property based Cryptanalysis. And we can see that for experimental Cryptanalysis, the complexity is low. While for division property-based cube attack, the number of rounds is very high. And the main contribution of this paper is a new cube construction algorithm, together with some heuristic new ideas on this topic. After a candidate cube was obtained, either Möbius transformation or three subset division property could be used to recover superpolis. The reason why we finally use Möbius transformation to recover superpolis is that a large number of subcubes could be tested simultaneously, while three subset division property treats superpolis just one by one. Thanks for your attention. This is my talk.
Thanks for your talk. So let's move to the Q&A session. So if you have any question, please post it to the Sleep. Currently, we received no questions so far. Yes. So maybe my understanding is very basic. So my question, I would like to have a very general question. So do you think your technique can be applied to other LFSL-based stream ciphers, or it's very specific to Trivium?
I think some of the techniques could be used to other NFSR-based street ciphers, such as the improved Möbius transformation and the idea of extend a small cube to a large cube. But for the starting cube set, I think it is specified for trivial, because trivial is a linear output function.
Thank you.
Well, I have a question, Tian. So how did you get the first cube? Is you ran for many experiments and then you chose one of them, or
the first what?
Yeah.
The first what? I did not follow you.
The cube that you started with.
Oh, the cube I start with. Okay. Could you see my slide?
Yep.
Yeah. For example, we first to predict the preference bit. The preference bit is one of the 6 bits. Assume S66 is a preference bit. Then we write the feedback function of S66 at the time instance t. The time instance t is the round you want to attack. Then it is expressed by the internal state of t minus 66. You can see that there is only one projected term. So the cube must be should be come from this quadratic term. Then a cube, if a cube is a linear, has a linear superpoly on S66, then it is necessary that some of the subcubes should have linear superpoly on S286 or S287 at the time instance t minus 66. And there are many such subcubes. I just randomly choose one of them.
Yeah, got it. Yeah, thanks.
Not at all.
Okay, if you have no more questions, let's move to the next talk. So thanks for your talk, Tim.
You're welcome.
Okay, the next talk is algebraic attacks on Rasta and Dasta using low degree equations, and written by Fukang Liu, Santanu, Sarkar, Willi, Meier, Takanori, Isobe, and Fukang will give us a talk.
Can you see my slide?
Yes, but
Okay.
could you do a full screen mode?
Okay, is it okay?
Yes.
Okay, thanks for the introduction. The title of this talk is Algebraic Attacks on Asta and Dasta using Low Degree Equations. So R* is a fully homomorphic, encryption-friendly, symmetric key primitive proposed at Crypto 2018. So this is a new trend to design such primitives. And the aim of R* is to achieve low end depth and end gates simultaneously. An important feature of R* is that their fine layers are different for each to be encrypted plaintext block. In other words, each key stream is generated with a different concrete R* instance. Specifically, we can see from this figure, the n-bit key stream Z is generated with different n-bit affine layers A, while the nonlinear layer S is fixed, which is the n-bit chi operation. Note that the chi operation, the 5-bit chi operation is already used in the K-round function. The designers proposed several parameters for R*. You can see from this table that the key size n is much larger than the claimed security level kappa. In addition, you can also observe that the number of rounds is very small, from 4 rounds to 6 rounds. In addition, the designers also proposed the 3 aggressive versions of R* called H*, where the key size is almost the same with the claimed security level, and the number of rounds is still small, from 4 rounds to 5 rounds. Now, before this works, there is no attack can break any of these ciphers, including R* and H*. So to analyze R*, there are some challenging problems. First, it behaves like a moving target. Second, the traditional techniques all fail because they require to collect many plaintext ciphertext pairs and a fixed encryption instance. However, R*, each plaintext ciphertext pair is obtained on a different encryption instance for R*. So this is the difficulty. However, there are also some exploitable features. First, the degree of the round function is very small, it's only 2. Second, the number of rounds is also very small. Third, there is a feed-forward operation, which implies a meet-in-the-middle style attack may work. The designers are obviously aware of these features. Indeed, they chose the parameters by considering the resistance against the linearization attacks. Specifically, the n-bit key stream Z can be written as nonlinear expressions in terms of the n-bit key, whose degree of these expressions is upbounded by 2 to the R, because the degree of the round function is 2. And the complexity of the linearization attack is directly related to the number of variables and the degree. So to improve the attack, we have to reduce the degree while keeping the number of variables the same. So I mean, so we should still treat the key bits as variables. So how to reduce the degree of the equations? One may consider the meet-in-the-middle style attack because of the feed-forward operation. However, can this really work? This is indeed, it is well known that the inverse of the largest scale cooperation is of very high degree. So if simply inverting the last cooperation will only increase the degree of the equation system, which will only increase the time complexity to mount the linearization attacks. So indeed, this is what the designers thought, and they directly gave up in this direction. Indeed, this is also what we thought in 2019. Yeah. So, but then how do we find the attacks? I think indeed you can find from this table that it is very simple, very, very simple. So I think it's more valuable to share how we find the idea. This is inspired from our work on low MC. So recover the secret key from a single plaintext ciphertext pair. So in this work, we started the low MC S box. Then in this work, by considering 2 consecutive output bits of the low MC S box, we can obtain 2 additional quadratic equations to describe this S box. So this then motivates us to consider whether similar analysis can be performed for the n-bit cooperation. To do this, we list the expressions for the cooperation. So Y0, Y1, Y2 plus yi minus 1. Then we consider two consecutive output bits, yi and yi plus 1. Luckily, and we immediately observed an useful equation, yi plus xi and yi plus 1 equals 0. So the last equation in this slide. So what does this equation imply? We should note that xi is the input of the car operation, while yi is the output of the operation. Due to the feed-forward operation, we can know that y can be written as linear expressions in the qubits, and x can be written as nonlinear expressions in the qubits, whose degree is bounded by 2 to the r minus 1. So according to this simple equation, we can directly construct a system of equations of degree 2 to the r minus 1 plus 1 to describe r round r star. So we reduce the degree from 2 to the r to 2 to the r minus 1 plus 1. This is in a word, we do not fully invert the large scale collaboration. Instead, we carefully consider some input bits and output bits. So this is what we do in this work. And then we are motivated to consider whether we have more such equations. Then we did experiments on the small scale collaboration to derive these equations and then test whether they can also hold for the large scale collaboration. In this way, we obtain these 5 equations. All of them can be used to construct a system of equations of degree 2 to the r minus 1 plus 1. So all of them can be used to improve the linearization attacks. So in summary, based on this simple observation, we could directly break 2 out of 3 instances of HR star. Second, the generic linearization attacks on Rasta and Dasta are all improved by 1 round for most instances. Third, Dasta is shown to be weaker than Rasta, thus violating the designer's claim. Most importantly, we believe this work sheds new insights into a large-scale cooperation and how to analyze the Rasta-like primitives. And there is also a simple question. So can we further construct nonlinear equations of the lower degree? So in this work, we almost peel off the last round. So is it possible, maybe, so can we do something similar to peel off, say, last 2 rounds? Yeah, if we can do it, we may break Rasta. That's all, thank you.
Yeah, thank you for your talk. So do you have any questions? If you have one, please post it to the Zulip. Yeah. So yeah, why do you call it a moving target in the page 4, slide 4 or something?
Yeah, because so each plain text, cipher text pair is obtained with different affine layers. So for the common symmetric key primitives, the affine layer and the nonlinear are all fixed, so they are stable. But in Rasta, for each plain text, they will be encrypted with different affine layers and the nonlinear layer. So this is why I call it a moving target.
I see. Thank you. Right. Do you have any other questions? So yeah, maybe I'm not an expert on this area, but it seems that this raster has one of the point is that the backward layer has a very high degree compared to the forward direction, and that's a design rational, and I think it's also effective to thwarting attacks in general.
Yeah.
That's an interesting,
point. It's an attack on the Rasta family, Rasta-like family. Yeah, but we may also consider if there is no feed-forward operation and we only truncate some output bits. The attack may not work, but I'm not sure whether we can obtain with some other techniques to obtain low degree equations. Maybe this is an interesting problem, but I currently don't have any idea for it. And there are indeed some constructions use truncation, not the feedforward operation.
That's a trending off to my point of to my idea, because by truncation we get shorter outputs simply. Yeah. Okay, so if there's no questions, let's move to the next talk. So thank you, Fukang.
Thank you.
Okay. So the third talk is automatic classical and quantum rebound attacks on AES-like hashing by exploiting related key differentials, written by Xiaoyang Dong, Zhang, Siwei, Congming Wei, Xiaoyun Wang, Fu, and Xiaoyang will give us a talk.
Thank you for the introduction. Can you hear the slides?
Yes, we can see.
So I'm talking about automatic classical and quantum rebound attacks on AES-like hashing by exploring the related key differentials. So in quantum clearing attacks, there are three generic algorithms. The first setting is that we have small quantum computer and large QRAM. Then the BHT algorithm will achieve the optimal trade-off. And then the second is the trade-off algorithm, and parallel row algorithm is the best algorithm. And the third setting is that we have small quantum computer but a large classical memory and no QRAM. Then thin S algorithm can achieve the best. In this paper, we are focusing on the rebound attack and its quantum version. So we first introduce the rebound attack. Rebound attack is proposed by Mendel at FSE 2009. So in the inbound phase, we're generating pairs conforming the inbound trio and with the meet-in-middle approach. And in the outbound phase, we verify those pairs to see if if it meets the outbound differential. And the outbound differential probability is PR. Then in classical setting, we have at least transverse 1 divided PR starting points to find a grid. So PR has to be large than 2 minus n2 and divided 2. In quantum setting, Hosoyamada and Sasaki apply the Rasta algorithm to find the right one. So they make the complexity by square root of 1 divided PR. And to be better than BHT algorithm, those time should be smaller than this. So PR has to be large than 2 minus 2n divided 3. Then to be better than Zhou algorithm, PR had to be larger than 2 minus n. In related key setting, we first find a related key truncated differential for EK and choose a pair, the K and K dot, which means the differential in the K schedule, and perform the rebound attack in the encryption data path with K and K dot. We build an automatic tool to find the related K differential. Different for in single K setting, previous work consider the probability of truncated differential. They enumerate the cancellations by MC and XOR operation to estimate the probability. But in related case setting, we have to deal another case. For example, in finger B, if we follow the previous method, we can enumerate the cancellations with two cells. But the total the probability of differential is can be just one cell. That is 2 minus C instead of 2 minus 2C. By this differential can be achieved by dedicatedly choose a K difference. So by using the degree of freedom from the K, we can increase the probability from this one to this one. So we introduce the constraints to deal with this condition, and we introduce the symbols, and for the degree of freedom, this equation is the consumption of the degrees of freedom. They should be smaller than the total degrees of freedom. The objective functions have two cases. The first case, we place two round inbound phase in the middle, and the objective is to minimize this one. And the second one is to place a 3 round inbound phase in the middle, and the function, the objective function is to minimize this. When applied to Symmetric, we have to deal with many incompatibilities because Symmetric's case schedule is very easy. And for example, this 4 round truncated differential, we can get one equation in this round, and we can get another equation with this round, and we can plus these two equations to find the contradiction. So this 4 round is incompatibility differential. To conquer these incompatibilities, we introduce a property of MC. Suppose these are the input and output of MC, and this is also the input and output of MC. And if there are at least 4 same cells in 2 vectors, then all the other cells should be the same. So we use this property to delete many impossible differential. At last, we find each round Symmetric each round related K differential for Symmetric, and we place 2 inbound phase in this part, and the outbound probability is 2 minus 211. Then we perform the quantum phase start clearing, and the quantum time to solve the inbound phase is about 2 to 22. And finally, we found the clearance with the Grover algorithm with time 2 to 1 to 9 S-box evaluations. Since there are 1 to 8 S-box applications in 1 H-round Symmetric, then the total complexity is about 2 to 1 to 2. It's better than poly-row algorithm. And we also find a 9-round Whirlpool collision. In previous work at Asiacrypt 2 Del and 2, Sasaki introduced the 8-round trio. And in the 8-round trio, only the case schedule paths have a full active rebound attack. And in our new trio, both the case schedule paths and data paths have the full state rebound attack. This is our trio. So to perform the quantum clearing attack, we define different functions. The first function is G, and this is to solve the 3-round inbound phase, and a Boolean function F is to identify a good pair, a good differential pair to satisfy the K, to satisfy this trio, the K. So given 36, we run algorithm on F to find a good pair satisfy the 3. Yes. So we define another function to identify 1 delta omega delta W6 if it is clean. The algorithm, the oracle for the quantum attack on 9-round Whirlpool is as follows. We run algorithm on UF to get the final clearing. And the attack for Whirlpool, the result is as follows. It's 9-round. And we also have some text on Saturday. Thank you.
Thank you for your talk. It's running out of the time slot, so we just move to the next talk. And if you have any question to this talk, and you can, still post to the jury, and we will, if we have a time, and we can have a question answer time for the rest of the session. Okay. Okay, I'll handle the task to the Sumanta. Is that okay?
Yeah, thanks, Kazuhiko. I take from here. Well, we have 2 talks remaining. So now we have clustering effect in Simon and Simeck. The authors are Gaëtan, Clara Parno, Andre Scottenloher, and the talk will be given by Clara. Clara, over to you.
Hi, do you hear me?
Yes, so we do.
Okay, thanks. So thanks for the introduction. My name is Clara Parno, and I'm going to present a joint work with Gaëtan and Andre Scottenloher, entitled Clustering Effect in Simon and Simeck. So Simon and Simeck are 2 lightweight block ciphers introduced by the NSA in 2013. Simon is optimized in hardware, while Simeck is optimized in software. The NSA tried to get Simon and Simeck standardized at ISO, but some experts from other countries were suspicious because it was the NSA. So more than 70 papers study Simon and Simeck. A little bit later, an academic variant of Simon and Simeck was proposed. This variant is Simeck. So in the following, we'll study Simon and Simeck. So Simon and Simeck are fested ciphers with a quadratic round function. So for Simon, this round function is composed of a rotation of 8 bits to the left, a rotation of 1 bit to the left, and both are ANDed bitwise, and the result is XOR to the right part. This is the nonlinear part, and there is also a linear part, which is composed of a rotation of 2 bits to the left. Finally, there is a key addition. So for Simon, there are 10 sets of parameters with different block size, key size, and number of rounds, and a linear key schedule. Concerning Simeck, the round function is very similar. However, the rotation amounts are different. There are 5, 0, and 1. There are 3 sets of parameters and a nonlinear key schedule, which reuses the round function f. So in this work, we study differential and linear cryptanalysis. Here, I will talk about differential cryptanalysis, but a similar approach can be done for linear cryptanalysis. So the goal of differential cryptanalysis is to find a differential, which is a pair delta delta prime, such that the probability that an input difference delta output a difference delta prime is bigger than 2 to the minus n, with n the block size. So to find such a differential, we will study the propagation of differences through every round. So first, through one round, this probability can be computed efficiently for Simon and Simeck. This was demonstrated by Kobel, Leander, and Thiessen at Crypto 2015. This can be extended to the probability of one trail. A trail is defined by all the intermediate differences, and the probability of a trail is just the probability, the product of the probability of each round transition. So this is for one trail, but if we want to compute the probability that an input difference delta 0 output a difference delta 4, we need to take into account all the trails. And as we can see here, there are many trails. So it is infeasible in practice to do the sum of all those trails. So for some ciphers, there is one or several dominant trails. So we can approximate this probability by considering only the dominant trails. But for Simon and Simeck, this gives not an accurate approximation. So we observed that Simon and Simeck have a very slow diffusion. So if we start with differences in a window of size W for Simeck, then after one round, we observe that the differences would stand in a window of size W plus 5 in the worst case, because the biggest amount of rotation is 5. However, this rotation amount 5 is associated to a nonlinear operation. So sometimes the differences will not propagate through the AND operator. So the differences will stand in a window of size W plus 1. So Simon and Simeck have a very slow diffusion, and we decided to exploit this. And our idea was to focus on trails that are active in a window of W bits. So it means that in place of considering all those trails, because it is infeasible, we only focus on a window on the trails that are active in a window of W bits, and this gives us a lower bound of the probability. So by doing this, we obtain some stronger distinguisher for Simon and Simeck. And then we extended this to key recovery attack. So starting from our distinguisher, we had some rounds before and after, and then we can evaluate the statistic of our distinguisher by guessing a subset of the key, and the total number of bits that need to be guessed need to be smaller than the key size. And this attack can be summarized as follows. So first, we need to find an efficient distinguisher. So this was done in the previous slide. Then we need to find a subset of the key that need to be guessed to evaluate our statistic. And finally, we will rearrange the operation to reduce the time complexity. So here we compare the differential and the linear attack for Simeck with a block size of 64 bits and the key size of 128 bits, and a distinguisher over 30 rounds. So what we observe is that our distinguishers are really similar. So for differential cryptanalysis, we have a probability of 2 to the minus 60.41. And for linear cryptanalysis, we have a distinguisher with probability 2 to the minus 60.36. So those two probabilities are very similar, and both distinguishers have the minimal number of active bits. However, for the step 1, the differential and linear cryptanalysis are really different, because for differential cryptanalysis, we are able to add 3 rounds before and 7 rounds after by guessing 123 bits, while for linear cryptanalysis, we are able to add 4 rounds before and 8 rounds after by guessing only 118 bits. So the linear attacks will be more efficient than the differential attacks. So here are our results. So for example, for Simeck with a block size of 64 bits and the key size of 128 bits, we obtained an attack over 42 rounds out of 44, while before the best attack only reached 37 rounds. So that's all. Thanks for listening.
Okay, nice talk, Clara. Is there any question? Yeah, so I don't see any questions, so maybe I can ask one question. So is this the simplicity of Simeck that is leading to this attack? Or yes. So is this the lesson that we learned that ciphers should not be too simple and they will be attacked?
Yes, probably. This is probably that, because there is the run function is probably too simple, and there is the diffusion is very slow. So this is probably not a good idea to design a very simple run function like the one of Simon and Simeck.
Right. So this is the trade-off actually. So when we design hardware efficient ciphers, then we go for like 2 degrees boxes and very simple circuit. But yeah, that's a trade-off. Yeah, good lesson to learn. So we can move to the next talk. Thanks, Kara, once again.
You're welcome.
Okay, I think only I'm left.
Yeah. So can you up your slides, please?
Just 1 second. Is it up?
Yes. Okay.
Okay.
So we're at the end of this session. So the talk is new attacks on low MC instances with a single plaintext ciphertext pair. It's co-authored by Shubhadeep Bonik, Khashayar Baruti, Sarj Badane, and Hailen Yan. So Khashayar will be giving the talk. What you, Khashayar?
So thanks for the introduction. I'm Khashayar from EPFL. I'm presenting the joint work with Shubhadeep Bonik, Sarj Badane, and Hailen Yan called New Attacks on Low MC Instances with a Single Plaintext Ciphertext Pair, or you see the name is long. I would prefer to call it that Cryptanalysis paper with a really long name. And I'm being the author with the hardest name to pronounce. So what do we do in this work? We study attacks on low MC in scenarios that are relevant to cryptanalysis of PICNIC. So PICNIC is a post-quantum signature scheme, which uses it's an MPC in head paradigm. So whenever you see the name MPC, you know that you want the minimum number of multiplications as you can. So we use block ciphers inside PICNIC that have low multiplication depth. And low MC is designed for this type of use cases. So low MC is used for PICNIC. So exactly what is the scenario that we're considering is that, so PICNIC's public key consists of a plaintext ciphertext pair. So we can only consider that we have a single plaintext ciphertext pair, and we're in the given plaintext ciphertext setting. And also each extra round when we do MPC computations counts. So we want to keep the multiplication depth as low as possible. So it's good to analyze variants of low MC, which have really low depth, multiplication depth, which means lower rounds. So looking at low MC, it's a simple SPN network. N is actually network in SPN. So it has a 3-bit S-box. As you can see, it's written there. It's a pretty simple S-box. And S-box works on 3 disjoint bits in every round. And then it's followed by an affine layer and the round key. So the only nonlinearity in the whole round would be the S-box. And then we have 2 variants. We either call it like a full S-box layer or a partial S-box layer, depending on whether there are some inputs of the round passing through the S-boxes, like all the inputs are passing through or some are not. So let's talk about data complexity 1 attacks that already have been done. The first work is by us. It's supposed to be presented in FSC 2022 because FSC was postponed twice. So in that work, we break up to the full round variant, we break up to 2 rounds. And for the partial variant, we break up to 0.8 N over S rounds. And then this year at Eurocrypt, Dinur presented an attack that only works for the full round variant, and it breaks up to 5 rounds. And for the 4 round variant, and for n equal to 129, it breaks up to 4 rounds only. Okay, so Dinur's algorithm uses some Fourier techniques and something called the multi-parity counting algorithm, and we use some linearization method that we will see in a second. So in this work, we will present a meet in the middle attack. For the full S-box layer, we will break up to 3 rounds. For the partial S-box layer, we will break up to N over S rounds. So the new attack uses the linearization ideas that we had from the previous work, plus some method that I call extend and linearize. We will see in a second. So what is the linearization? This is an informal version of the theorem that we had in the previous work. So it says that if I guess the output of any quadratic function, any balanced quadratic function in the input of the S-box of low MC, I can linearize the S-box. So for instance, I can take the majority function, the 3-bit majority function. If I guess the majority of the inputs of the S-box, I can linearize the S-box. So inherently for a round, if I guess the majorities of every single S-box that I have in that round, the whole round becomes linear. Okay. So now let's see how the attack works. So we use an MITM attack that was proposed, a meet in the middle attack that was proposed in the previous work. So the idea is I will break my key into 2 parts, K1 and K2. And for all the rounds other than the first round, I will guess all the majorities of every S-box input and linearize all the other rounds. Then I do a forward propagation to get an equation of this form and a backward propagation for the last rounds. and get an equation in this form, which left-hand side is only in K1 and right-hand side is only in K2. And AI and BI are linear, they come from the backward propagation, and FI and GI are quadratic and come from the forward direction. Now what I will do is that I will also divide my K2 into 2 parts. And the point is, although these functions are quadratic, they're really sparse quadratic functions because how the LOMC box works. So what I can do, I can relinearize, I can extend my space and relinearize these equations and get some linear equation over a bigger space of this form. Now my left-hand side is not full rank, so I can compute the kernel of it. Let's call it H. And then I get an equation like this in the 2/2 of the second part of the key of K2, which this is perfect to mount a meet in the middle attack. So exactly, I do a collision search attack type of thing between K2.1 and K2.2, and I keep a list of all good K2 values that I have. And then I do a meet in the middle between K1 values and K2 values that are already in this list. So as you can see, at each part, I'm only guessing 2 to the power n over 3 values of the key, let's say. And for the partial round, I can do something similar as well. Here it's more delicate, like it needs way more, it has way more details, but simply the idea is similar. I will split my rounds into the first A rounds, then the B rounds after, some rounds in middle, which I call the middle rounds, and then the last C rounds. And what I will do is that I will linearize the middle rounds by guessing the majorities. Then I will extend the space and relinearize every equation that I found based on the equations induced by my cipher. And then I will do 2 meet in the middle attacks. First one is between Ka and Kc, so the first rounds and the last rounds. And the second one is between the good values that I have for Ka and Kc and the Kb values. Okay, so let's conclude this. In this fork, we propose attacks for both full layer S box and partial layer. For full layer S box, we break up to 3 rounds. It's not very impressive, but we have the fastest attack for the 2-round variant. But we have the benchmark attack for the partial layer S box. So we can break up to n over S rounds, and we have the fastest attacks for all the partial layer variants. And to wrap it up, we should not go on a picnic on a rainy day. So make sure that you choose your parameters smartly when you're using block ciphers with low multiplication depth. Thank you very much for listening.
Okay, thanks, Kashar. Any question? I don't see any question. Kashar, so you have more works on this LOMC attack is coming up, right?
Yes, there is some ongoing work at the moment on LOMC as well.
So how serious the now LOMC is now in respective of those attacks?
It's really hard to say because it's a real trade-off between how many rounds you want, because if you're looking at Picnic, if you're considering the use case in Picnic, it's really a trade-off between how many rounds you want, because how Picnic works to give like a high-level idea. So the prover, so we have a proof of identification system that the prover is simulating an MPC computation. So it's dividing the secret key into shares and then doing an MPC encryption in like an MPC, doing an LOMC encryption in an MPC manner. So every round that you add, you will add more multiplications, and then you will have a huge overhead on your prover, which is your signer in the end. So it's a real trade-off. So I think, as I said, the Noor's algorithm breaks up to 5 rounds. So the current thing that we have, we might be able to go up to 7 rounds, I guess, but the difference with exhaustive search is really not that much. So I'm not sure if it's really concerning. But yes, I think they're like ongoing work on this MPC and head signatures, follow-ups to Picnic, which look more promising, I would say.
Right. Yeah. Thanks for these comments. Yeah. Any question? Okay. If not, then I thank again Kashar for this wonderful talk.
Thank you.
So we see that we have still time for more questions. If you have from the previous talks, we can have those questions. Please go ahead. So I have the question on this quantum rebound attack. Can I have the author, please? Xiaoyang, are you there?
Yes.
Yeah. So you have this attack. I'm just not expert in quantum, but just wondering what about the experimental validation? So is there any simulation available there?
Sorry.
So you applied Grover, right?
Yes.
Yeah. So I'm just.
What's the Grover algorithm?
Yeah. So is there any experimental validation of the quantum part that you did?
You mean post-quantum? Sorry, I can't. I don't follow you.
Is there any simulation result on the quantum part of your attack? Or we have to wait until the real quantum computers available for this attack to validate?
Sorry, I can't follow.
Oh, okay, we can take this question offline. Fine, thank you.
Okay, thank you.
Kazuhiko, you want to say something?
Yeah, I have one short question about the Simon Simeck attack. Right?
Yes.
Okay. So yeah, it seems that an idea of limiting the window to the focusing on the possible differential and the linear characteristic seems a very generic idea. And how do you think that an application to other ciphers for this idea, or did you see any similar work on other cryptanalysis on other ciphers?
I think it's not easy to apply this to other ciphers because here it works well because there is only rotations. There are no other mixing between the bits, because if there are some mixing steps, then it will not work. But probably for the cipher T, I don't know exactly how we pronounce it, TEA.
T.
Yes, we can probably apply something like that, but we didn't look in details.
So basically, possibly applicable to very simple cipher, like consisting of the addition, rotation, the next, or sort of this simple logical operation. All right. Yeah. Thank you.
You're welcome.
Any more question or any discussion you would like to have? If not, maybe Kazuhiko, you can end this session and go for a break.
Okay.
Yeah. Okay.
It's almost time. So yeah, thanks for joining this session, and thanks for the wonderful talk for the presenters. Okay, so thanks, and let's move to the what the next program is. I haven't checked, but then let's move to the next.